So let's talk about matrix sums and scalar multiplication. So here's our definition. Suppose A and B are matrices of the same size, m by n. Then the sum, denoted A plus B, is the m by n matrix whose columns are the sums of the corresponding columns of A and B. So in particular, if A has columns A1 up to AN, and B has columns B1 up to Bn, then the jth column of A plus B is AJ plus BJ. So for example, let's consider the sum of these two matrices here, A and B. Well, then A plus B, the first column of A plus B, is going to be 3 minus 1 and a 1 plus 4, the first column of A plus the first column of B. The second column is the second column of A plus the second column of B. And the third column is the third column of A plus the third column of B. And then we do the arithmetic and get 2, 3, 0, 5, 1, 7. So note, if A and B are different sizes, then the addition, the sum, is undefined. We don't try to add matrices of different sizes. So suppose A is an m by n matrix and C is some scalar, then the scalar multiple, it's denoted C times A, just by concatenation, is the m by n matrix whose columns are C times the corresponding column of A. So the column is just the scalar multiple C times that column of A. So for example, if A has columns A1 up to AN, then the jth column of CA is C times AJ. So let's consider this example where A is a 3 by 3 matrix, given here, and C is the scalar 3. Then CA, the first column is 3 times the first column of A, second column is 3 times the second column of A, third column is 3 times the third column of A, and then we do the arithmetic and get that. So here's some properties that hold. These properties show you that it makes sense to denote these operations as addition and multiplication and think of them as addition and multiplication. They basically say that the operations behave the way you would hope. Okay, so let A, B, and C be three matrices of the same size, m by n for concreteness. Let R and S be scalars. Then A plus B is B plus A. And so this is just saying that the matrix sum is commutative. 2, A plus B plus C is equal to A plus the sum of B and C. And so notice this is just saying that matrix sum is associative. 3, A plus the 0 matrix, so the 0 with an underline, I'm going to use that to denote the 0 matrix, is equal to A. And that's just saying that the 0 matrix acts as the additive identity op. 4, R times the sum A plus B is RA plus RB, is just saying the scalar multiplication distributes over matrix sum. 5, R plus S times A is RA plus SA, and so notice this is a different sort of distribution property, but this also holds. So scalar multiplication of matrices distributes over regular addition in the real numbers. And 6, R times S times A is the same thing as R times S as real numbers times A. And so one of the things to think about is how we might go about proving such statements are true, right? And so let's prove A plus B equals B plus A. So you get a sense of what proofs look like in this setting. And so what we're going to do is we're going to prove that the columns of A plus B are the same as the columns of B plus A. And then that'll show that the two matrices are the same. And so we have to give the columns names. So let A be have columns A1 up to AN, and let B have columns B1 up to BN. Then the jth column of A plus B is AJ plus BJ by definition. And AJ plus BJ is equal to BJ plus AJ since vector addition is commutative. The jth column of B plus A is BJ plus AJ, again by definition, and so the jth column of A plus B is equal to the jth column of B plus A. And that holds for all j. There's nothing special about the particular j we picked. And so therefore all the columns of A plus B are equal to all the columns of B plus A, and so we can conclude that A plus B is B plus A.